Hello, this is Dr. Christy Patton-Lukes, Chemical Engineering Professor at Missouri S&T. In this lesson for process control, in this video we're going to be continuing our study of Chapter 4, looking at transfer functions and block diagrams and how these can give us a full story of our systems. Let's look specifically at transfer functions. After the last video, I had suggested you go back and look at some of your previous Laplace transforms of differential equations and see what you could kind of glean from that, okay? In general, what you end up with is that you have something where it's some sort of polynomial in S in the numerator and a polynomial in S in the denominator. Now we might have it in a factored form or whatever, but we know that that's just a polynomial, right? So the polynomial in the numerator will be to the m power, the one in the denominator will be to the n power. And then I need to talk about those coefficients. Our general form is that we rewrite these by transforming it so that the numerator and the denominator, those polynomial forms, are both something plus 1. The s to the 0 power is going to have a coefficient of 1. And when I do that, the leftover multiplier for all of that in the numerator is going to be something that we are going to identify as the steady state gain, and we're going to just name it capital K. All right, that's going to be our symbol for steady state gain, no matter what the rest of those polynomials looks like. Okay, and so if we do that, we're going to have some sort of transfer function written in this form here, where I'm going to have that gain times a polynomial to the power m ending in 1 and divided by a polynomial to the power n ending in 1. Now, it turns out that I can definitely say that for any physical system, n has to be greater than or equal to m. Okay, so it's not going to be physical if n is less than m. So we're going to have a larger polynomial in the bottom than in the top. Often we're also going to find that in the numerator, m is 0. So all we have in the top is this k term. Okay? Whenever we do have a polynomial in the numerator, we're going to describe it as it has numerator dynamics. Okay? Turns out those numerator dynamics are coming from our forcing functions in the original differential equation model. The other thing that as you looked at these, such as in the example that we did together, transfer functions are additive. So I can look at the two different input functions and I can multiply these by their transfer function and add those together to get the net effect. Now we also have been looking at the rules for going through block diagrams, and when we go through a block, we multiply, right? We multiply going through here. Well, if I had another process, maybe it went through tank 1 and then it went through a second tank where something different happened to it, I'm going to multiply again, okay? And then I can take these and I can add them to another transfer function, okay, or input function. Those to get y. Let's look at an example, okay? So I have input functions x1 and x2. I have some transfer functions that I've just labeled g1, g2, g3, and g4. And what I want to do is see what is the net y of s for this. So what was that Laplace model I would have gotten for this diagram? Ultimately, we're going to be wanting to go the other direction, COY, and create the diagram. But we're going to start by looking at a diagram and figuring out what y should have been. So first thing that happens is we've got x1 here, and it's going through and it splits. So what happens when it splits? Now this is a signal, okay? This is just a description of the flow rate, the composition, the temperature, whatever. The signal is not going to split and be like smaller. When a signal splits, it's going to be the same. So this is going to be x1 and this will be x1. And so therefore, when I get here, this is x1 times g1. And here, this is x1 times g2, right? I multiply as I go through a block. I'm now coming to an adding block, which says that I'm going to do plus the top one minus the other one. So what I end up with coming out is that y1, that's what's coming out, is going to be x1 g1 minus x1 g2. Okay. If I want to get to y3, I'm taking my answer to y1 and multiplying by g3. And so therefore it's going to be g1 g3 x1 minus g2 g3 x1. So that's y3. Now I'm to another adder block, but what I'm adding is got this complication. So let's follow the streams here. So x2 is going to come and it's going to split. This time it's going to go through g4. Okay, so this is x2 g4. And this one is just going to be no multiplier, doesn't go through a transfer function. And I'm going to be subtracting it to get y2, which is going to be g4 x2 minus x2. So I have y2, I have y3, and to get to y, I just simply need to add those. So y of s will be y2 plus y3, which is g4 minus 1, x2 of s, plus, let's see, that was y2, y3 was g1, g3 minus g2, g3, x2 of s. I could write these as overall transfer functions. Well, y of s over x2 of s is g4 minus 1, and y of s over x2 of s equals g1 g3 minus g2 g3. Okay, so I can simplify this if I wanted to and write this in terms of x1 g4 minus 1 and add to that g3 times g1 minus g2 and this is x2. And this is equivalent to this. Okay, go through, make sure you agree with all of that math. We're going to, in the next lesson, do a little bit of a harder block diagram and simplify that. Thank you for your time.